What's important for us in the context of this study is that DNSSEC is going to introduce digital signatures in DNS responses, known as eDNS0 or DNS extensions. We need to remember that as DNS gets introduced, so does this trade-off. So because on one hand of the scale, we are adding security with these DNS extensions, but on the other side, we are creating larger response sizes in general for most queries. So that is the trade-off that gets introduced with DNSSEC. Let's pivot over to talking about distributed denial of service, DDoS attacks, before we talk about how the two are related. So these high volume attacks are generally going to rely upon some shared principles. The first of which is IP spoofing. IP spoofing occurs when an attacker falsifies the IP address inside of a request. And what that leads to is actually the second bullet on this list, because once the attacker falsifies that IP address, the corresponding response is also sent to that falsified IP address, and that is when reflection occurs. And the third thing that we need to consider in the context of DDoS attacks is something called DNS amplification. So some network protocols are going to return a large answer to a relatively small request. So when DNS returns a response where the size of the response is greater than the size of the query, that is the phenomenon of DNS amplification. And in order to analyze how DNSSEC imposes a risk on DDoS attacks, we actually need to exclusively focus on one type of DDoS attack, and that is a DNS amplification attack. What is a DNS amplification attack? It's exactly what it sounds like. So an attacker is going to use bandwidth amplification. Notice down in the bottom right in that blue box, we define a new metric called amplification factor, which is defined as the response size over the query size. So that's how we're going to be measuring the amplification of certain queries. And for a DNS amplification attack, there is a couple common methods that attackers use to perform these attacks. So one very common one is the crafting of custom domains. If I'm an attacker, these are domains that I'm crafting that I can guarantee for certain queries that this domain is going to return a large response. So maybe I am designing a custom domain for which if any TXT queries are sent, I know this domain is going to return a sizable TXT record. And that is a way that attackers can ensure a high amplification factor. Another very common practice, maybe the most common practice, is the use of any queries. So remember, any queries are going to respond any record found for a query sent, any record type. So the response for any queries are going to be generally the biggest responses we're going to get, which makes them very attractive to attackers who are performing an amplification attack, because again, they want to achieve that maximum amplification factor. And so that is what brings us to our motivation, because we can see that the introduction of DNSSEC and larger response sizes clearly creates the potential for high amplification, because with larger responses, you also have higher amplification. So there is a clear potential there. The motivation for this experiment and the reason why this study is performed is because the question then becomes, how bad is it? We can see that there's a clear risk, but how bad really is DNSSEC for the potential for DDoS attacks? So now let's pretend we're an attacker before DNSSEC. Because before DNSSEC, there were some challenges that attackers ran into. So if I'm an attacker and I'm trying to perform a bandwidth attack before DNSSEC, I would run into some challenges. First of all, the bandwidth on the open resolvers that I'm going to be using for my attack might not always be guaranteed. That bandwidth can be scarce. And second of all, if I'm crafting my own custom domain for this attack, that brings two risks. One, I'm going to be more vulnerable to prosecution as an attacker. It makes myself more vulnerable. And also the domain itself is actually more vulnerable to be taken down, which would compromise my attack totally. And lastly, victims and clients can implement some sort of response filtering for crafted domains, which also is going to hinder our amplification attack. But now let's see what happens when DNSSEC is introduced, because attackers are definitely going to benefit from DNSSEC being introduced, because after DNSSEC, if I want to do an amplification attack, I don't have to create a custom domain anymore. I can now choose from a collection of DNSSEC signed domains. Right now on the internet, there's about 3.5 million DNSSEC signed domains floating around out there. And by choosing one of those domains, I'm going to be, one, less vulnerable to prosecution, and the domain itself is going to be less likely to be taken down. It's a little more stable. And lastly, these signed domains are also going to be a lot harder to filter for victims. And there's one last thing I want to point out. So remember that DNS extensions and eDNS0, they vastly increase the potential for amplification. So my question would be, what is the max amplification that an attacker can achieve before DNSSEC and before eDNS0? And the answer to that, how we're going to do that, is we're going to take a query for the smallest domain name imaginable. Let's take x.com. This is going to yield a query size of about 23 bytes. And then secondly, let's assume a response size that before DNSSEC, the maximum response size for a DNS response is 512 bytes. So if we use those two measures, that's going to yield an amplification factor of 22.3. So that is going to be our pre-eDNS0, pre-DNSSEC maximum amplification factor. And that's going to be pretty important because we're going to refer back to that as we keep moving forward. So now let's take a look at our experiment, how we're actually going to quantify how bad DNSSEC is. Our first step is we're going to perform a detailed measurement on a large data set of DNSSEC signed domains. When I say large, I do mean large. I mentioned there were 3.5 total signed domains floating out there. This study is going to cover 2.5 million. So roughly 70% of all DNSSEC signed domains are going to be covered by this study. And then once we take those measurements, we're going to compare them to the measurements for a representative set of non-signed domains. So we can kind of see the risk for amplification in signed versus non-signed. And we're not just going to do it with one query type. We're going to do it with a whole wide array of query types. We talked about before how any queries are the most common. And you can see your any query up at the top right there. But we're also going to use a slew of other queries as well. For example, MX. We expect domains, signed or non-signed, can have one mail server or they can have multiple mail servers. So before going into this experiment, it is reasonable to assume that these query types might also return response sizes that are big and yielding high amplification factors. So we're going to test all these query types. And over there on the right, we have two DNSSEC specific query types. The first one is DNS key, which is going to return a set of public keys required to validate signatures for a certain domain. Domains can have one up to multiple, 3, 4 are also common numbers of DNS keys for a singular domain. And the bottom one there, NSEC, is not so much a query type, but it's the record type that is returned when a signed domain doesn't exist. We're going to call that authenticated denial of existence. So now we're going to move into how are we going to measure this? Like, how are we going to quantify how bad it is? What are our measurements, our metrics? And there are actually a lot laid out in this study, but I want to focus on a couple for our sake right now. Let's look at the top three. So we have our response size and our query size. And as you remember, given those two, we can easily calculate our amplification factor. And here for this study, our amplification factor is definitely going to be our main metric. It's going to be our main comparison of these two different types of domains. And now let's talk about how. We know what we're going to use for the measurements. How are we actually going to do that? There's two crucial pieces of software for this study. The first is a zone file parser. So given the size of a DNS zone, we're actually going to use 6 different TLDs. It's going to extract both DNSSEC signed and regular non-signed domains, and it's going to store those domains inside a database. And after that, the second piece of software, the scanner application, is going to operate on that database, going down through each domain, performing those queries that we laid out in the previous section, and it's going to record those measurements for us as well. Before we get into the actual numbers, a quick ethical note. In this study, when the study was being performed, particular care was given to ensure that our measurements that we're performing don't impose an unnecessary burden on the authoritative servers that we're scanning for this data. So let's get into the data analysis. And the first key thing to remember is that amplification factor is going to be the main metric here. And the first data that we're going to look at is actually our any queries. So this is the amplification for the query type any. And on the left-hand side, that gray filled-in peak is all of our non-signed domains. And then on the right-hand side, those colored bars right there, each colored bar represents a different TLD. This represents all the TLDs used, and this is just the amplification factor for all any queries. There's lots to unpack. The first thing I want to point out is first, let's look at our unsigned domains. The average amplification factor for our unsigned domains is going to be 5.9. And right off the bat, we're going to compare that to the average for signed domains, which is 47.2. That's our average right there. So we can immediately see right off the bat that assigned domains are going to have more potential for high amplification factors. And the last thing I want to point out here is that vertical line down the middle, which represents that 22.3 that we calculated earlier. That's going to represent our pre-DNSSEC upper limit for our maximum amplification. So that's going to be our upper limit. And for this case, we can see that for any queries, almost about 100% of signed domains, if not a vast majority of signed domains, lie above that upper limit. And that is not good news for us. That is telling us that the introduction of DNSSEC in these signed domains are definitely giving us more potential for amplification. The next two that we're going to look at are our DNS key and NSEC, our DNSSEC specific query types. The first thing I want to point out on this graph, let's look at DNS key. 37.8% of DNS key queries are above the upper limit. So it's not quite as bad as any, but that is still not good news because attackers that are going to use DNS key queries can clearly achieve an amplification factor that is above that upper bound. With NSEC, on the other hand, is not as bad as some might have expected. Most of those queries, as you can see, are going to fall to the left, which is in bounds of that upper bound that we laid out right there. So DNS key is better than any, but it's still bad. Let's keep pushing forward. And now we're going to look at some of our more common regular DNS queries. So here we have your TXT, your MX, your NS, and your AN quadruple A queries right here. And you can take a second to look at all these graphs. And the first thing I want to point out is that here on this slide, we're getting some more good news because a majority of these queries, whether they're signed or non-signed, most of these queries are falling below our upper bound. So we can see that there is some nuance to this risk of DDoS attacks with amplification. The second thing I want to point out, I want to specifically draw attention to the MX and NS queries. I mentioned before we performed the study, it was not crazy to assume that these types of queries with mail servers and more than one authoritative server would return fairly large responses, but in fact, that was not the case at all. And these two types of queries were actually significantly lower than the rest of them. The peaks were at significantly lower values than the rest, which was some good news for us. So, conclusions. What did we learn? What have we learned from these graphs? First of all, I think it is safe to say our overall conclusion is that DNSSEC is bad for distributed denial of service attacks. If we only consider any query type, the amplification factor for DNS domains exceeds the amplification factor for regular domains by about 6 to 12 times on average. That is a lot. That the amplification factors are way higher for our assigned domains. For specifically the DNS key query type, about 40% of those queries are above the upper limit, which again is very dangerous for DDoS attacks. And in general, it seems like DNSSEC is giving our attackers more options because it is clear that before DNSSEC, amplification attacks are definitely possible through the creation of custom domains and stuff like that. But when you introduce DNSSEC, we seem to give attackers more options and more variability in how they're performing these attacks. They can now use signed domains and DNS key queries, so we're giving them more options. And as we discussed, there is some nuance to this risk because many of our common queries yielded amplification factors that were well within our upper bound. Now let's talk about countermeasures. How can we prevent this? And going forward, what work is there to be done? There's a couple ways. The first one we'll cover is ingress filtering. Ingress filtering is simple. It's just blocking IP spoofing. The caveat about this countermeasure is that it only works if it's deployed internet-wide, which it is not and is not that feasible. So while it is effective at blocking amplification attacks, it only works if it's deployed internet-wide. The second is response rate limiting. Pretty straightforward. Your authoritative servers, if multiple responses are being sent to the same IP block, it's going to limit the rate of outgoing responses. The third one down there is eDNS0 cookies. And this one is actually one of the most promising countermeasures going forward. It's not fully deployed right now. It's not fully functional right now. But this eDNS cookies introduces some sort of address authentication. So your authoritative servers actually aren't going to include the DNS extensions. When they send the response back, they're not going to include the extensions until the user provides some sort of cookie or authentication to that server.